Transition away from this, we're going to talk a little bit more about the Gibbs energy. The next two spots we're going to talk about are standard molar Gibbs energy. So looking basically back in those tables and calculating things. And how does the Gibbs energy change with temperature? So the general chemistry equation, delta G is equal to what? Yep, is saying what's being held constant here. There are two things. Pressure, yep, and what else? Temperature, yep. Pressure because there's an H here and it's Gibbs. Temperature because there's not a delta here, right? But what happens when you're looking at a situation when temperature is changing? For example, in the human body, if you give a drug or you have a protein, does temperature stay the exact same throughout? No, it's going to fluctuate. And it's going to have an impact on delta G. If things are going to fold, unfold, if it's going to bind, or it's just going to stay there. Is it ever going to leave? So knowing those things and those thermodynamic properties is extremely valuable for pharmaceutical companies. Their experiments are always great associated with that, but they're doing tons of calculations to figure out those values and how G does change. So that way they can screen through literally billions of possibilities and maybe end up at hundreds of thousands of possibilities. Okay, so let's talk about the boring one first. Or maybe the less boring one. I don't know. It depends on what you think. The easier one. Let's talk about that first. You know, on the hazards for our jobs, they actually say inhalation of chalk dust. Yep. Most universities say if you get a lung condition, you can't sue based upon the work hazards. Very different. All my family were like farmers, like factory workers and stuff, where people get crushed all the time. And my big worry is like cancer from sniffing too much benzene and mesothelioma from chalk dust. Like, come on. Okay, standard. What is meant by the word standard? Yes. So we're talking about one pressure. What's that one pressure? Yeah. 1 bar, 1 atm-ish. And then what's the other thing that we said was consistent? Temperature. It's one temperature. The temperature generally is indicated. It's usually 298, but it changes. You always want to check in whatever reference you're looking at for whatever temperature you're considering. We're considering delta G naught of a reaction. What else would this be equal to? Let's apply our Gen Chem stuff. What else would it be equal to? Yeah. So got products. And what type of delta G is that? Yep, F. What does the F stand for again? Yeah, formation of whatever we're considering minus, what's the other stuff we got? Yeah. Okay. Looking at that, why, when we were considering entropy, we didn't have deltas here, right? Why do we have deltas here now? Yeah. Yep, delta G can't. And why can't delta G be found directly? From Gen Chem, delta G is equal to what? Yeah. Okay. We can solve for that directly, right? What can't we solve for directly? Yeah, delta H. We have to have that in terms of a reference. So let's talk about these Gibbs energies of formation. Delta G. Okay. So just like you guys said, delta H is in here, so we have to talk about changes. When we're discussing the heat of formation, what are we talking about the change from? The reference states. And what's the reference state going, or could you give me an example of a reference state? Yeah. So delta G F naught of O2 gas. What's that equal to? Yeah. So what we're saying here is we're starting from a reference state, its constituent elements, and moving up to whatever the compound, or down to whatever the compound is. So start from reference states, where delta G F naught of that state with a 0. And I guess we should be a little more formal. We should put a line above these things. For talking about it in terms of a molar heat capacity. You could do an also like a sub M. Your book a lot of times does a sub M. I like the line on top because it's easier. All right. Do we want to go through the calculation of one of these? How many people want to do that? Raise your hands. 2. Anybody else? No. Okay. People want to do it. We're doing it. All right. What sounds better? Dinitrogen pentoxide or iodine? Okay. All right. Yeah. The other one's super poisonous, though. It's fun. All right. Example. Calculate delta G naught reaction for HI gas plus O2 gas. I2 gas. At 298 K. And we're also going to ask, will this reaction happen spontaneously? Yeah, this one's a little tougher. Okay, what are we looking for? Yeah. Okay. What do you suggest we do first? Yeah, we can look up the G of formations for each of these things. How's that going to get us any closer to that? The delta G of reaction. Yeah. Products minus reactants. So we need a product. Give me a product. Iodine. We got to do 2 that I2 gas. What do we know about that one though? Yeah, it's 0. No, it's not 0. I lied. Anybody know how iodine's found? Not as a gas? It's a solid. It's really weird because it sublimes though. So yeah, you have this purple cloud of gas. Like whenever I open the iodine to make it for your guys' lab, it's purple gas coming through. It's really pretty. Yeah, yeah, exactly. I think they're pretty cool too. Ooh. I like the coinage metals because they make me rich. Actually, the next column over, platinum and palladium, without those 2 things, we would like seriously all not have the comforts of life that we have. So those are pretty good. That's tough. Halogens are really cool though, because you can make things that get so hot that, like, what was it? I think they made this compound once and it caught concrete on fire. You have to get really, really hot to burn concrete, and that stuff can. It's not that hard to make either. Don't make it. Yeah, the other cool thing with iodine is too, if you put it in a vessel and you, like one of the Florence flasks, and you have solid iodine, you get vapors that come up, and if you heat it up, you can turn it all to gas, and then if you cool it down, you'll get iodine crystals that all form on the inside of it. Maybe I should do that. It's cool, and they're pretty purple. They're like metallic. Stare at iodine the next chance you get. What else do we got here? Back to what we were trying to do. Yeah, water. That's boring. Go back to talking about solid iodine. Liquid. Okay, what else do we got to do? Yep. HI. Gas. What is the name of that compound? Oh, I know, Gen Chem. Yep, hydroiodic acid. So what's this? Yeah, it's just hydrogen iodide. And then what else do we got? Yeah. Yeah, good old oxygen. Looking at this, do we have to look up the values of all of them? Which one do we not have to consider? Yeah, because what's the value of it? Why is that 1, 0? Reference state. I was being tricky here. I even didn't think that was I thought that was the reference state for a second. It's not. If we were looking at any of the other ones like bromine, what would bromine's reference state be in terms of physical states? Liquid. Yep. It's one of the few ones that's a liquid. That one's really scary to work with. Yeah. Bromine. What's the only other liquid that's on there? Yeah, mercury. Gallium is a solid. It's really cool. You can hold it in your hand and it will turn into a liquid. I have solid gallium downstairs. I'll bring it up sometime. You can use it to get into safes. Do you guys know what an amalgam is? Oh yeah, yeah, like with like mercury fillings and stuff. If you take gallium, you can get it into a liquid and then it will dissolve into other metals and make them really brittle. So you can just break it right open. You can just fold the metal open. So you ever really need to get into a safe? Yay, crimes. All right. All right, we can look these things up. Not too bad to find. What units do you think we're going to have here? Yeah, per, yeah. Plus 2 times positive. Ooh, that one's small. When you sum that all up, I get negative 442.4 kilojoules per mole. Is this reaction spontaneous at ambient temperature and pressure? Yes. How do you know? Delta G reaction, how would we have to compare that? Yeah. So it should be thermodynamically spontaneous. All right. We don't have enough time to start the next portion of things. What's the downside to this? The calculating delta G reactions this way. We got to know the reference values, so that creates a problem. What's the other issue? Yeah, because how often do we really work at 298? Like sometimes in our lab because the HVAC system isn't fantastic. That's pretty hot though. Like I think that, what does that work out? Let's do the math real quick because I can't remember. What is it? C is equal to 32.5/9. Okay, move that around. 32. So can someone calculate? Anybody got a calculator off the top of their hand? Top of their hand? Top of their head. Can you figure out what 25 degrees C is? I feel like it's like 77 Fahrenheit. Is it? Is it 60? It's 77? Okay, that's too hot for me to want to work. I will go home and not work in that type of temperature because I'm a dainty flower. That's hot. The other thing is if you want to look at it in terms of living creatures, are living creatures at 77 degrees Fahrenheit? No, so everything biologically related out the window if we want to look at it this way. What do we know about delta G? How's it defined? Yeah. So what impacts it? Temperature, yep. Pressure will too in here. So delta G will change, which, you know, changes the equilibrium constant and changes will it or won't it be spontaneous. So we only have one temperature and we only have one pressure to check out. Pressure really doesn't impact us too much in lab because we can kind of keep it consistent. Temperatures make a big deal though, depending on what system we want to look at. And if we want to be able to predict if it will or will not happen, we're going to have to look at something deeper than this and something deeper than that. So next time, that's what we're going to consider. We're going to use, I think, one of the Maxwell relations to look at that. And someone had a joke about, or a meme about how PChem is nothing but a line. It's true. We're going to make a line to figure this stuff out. Okay? Oh, boy. All right. You guys have an awesome day. I'm going to be here for about like 15, 20-ish more minutes, and then I got to go home. Okay? If you need me anytime for the rest of the day, I can try to Zoom, assuming everything is somewhat calm in my house, or I can answer things by email. Okay? Tomorrow morning, I'll be here all morning, starting at like 9. So if you need to communicate then or need additional help, I'll be around. And if it's something for your labs that you need, we can discuss it in lab, and we'll make it work that way. Okay? All right, have an awesome day, guys. We'll see you tomorrow.
Ask us a science question.